So I cut the last video short because my son started freaking out about Ellen's Game of Games. We scan the coin when we watch it, and he could not scan it by himself, and so he kept interrupting me. But I did want to point out, and you probably may have heard me say that before the video cut out, but anytime you have a 1-to-1, meaning one cation, one anion, then the KSP expression is always going to be S squared, no matter what. Anytime you have a 1-to-2, can be cation, anion, cation, doesn't matter, as long as it's 1-to-2, the KSP expression is always going to be 4s cubed, no matter what. All right, so let's go back to that problem that I took out at the beginning and answer it now. So we're going to use a little bit of information about K and a little information about Q and determine if a precipitate is going to form. So first, we have to understand what we're forming. So we have calcium nitrate reacting with sodium fluoride. So we're mixing two salts together. They're going to undergo a double displacement reaction, forming calcium fluoride and sodium nitrate. So I'm going to balance it out this way. And then if you remember back last semester, we talked about solubility rules and we had a whole chart for that. Well, this is how we're going to determine that this is going to stay aqueous and that's going to be the solid. So this is what we're concerning ourselves with. Will calcium fluoride precipitate? And we can use Q to tell us that by establishing its relationship to K. So essentially, we're looking at the solubility of calcium fluoride. Is it super insoluble or is it super soluble? So we need to determine what's the concentration of calcium fluoride. Sorry, I left that 2 off there. I just snuck that in. Of the calcium fluoride once we mix calcium nitrate and sodium fluoride. So I'm going to react calcium nitrate, and the volume I'm given is 0.01 or 0.100 liters. For every 1 mole of calcium nitrate, I can make 1 mole of calcium 2+. That comes from this. That's the relationship. Meaning I'm going to have 0.03 moles of calcium around to form calcium fluoride. And I'm going to do the same thing with fluoride. All of the fluoride I have is going to come from my 200 milliliters of, why did I just do that? Sorry, it should be on the top. My 200 milliliters of sodium fluoride, and for every 1 mole of sodium fluoride, I can make 1 mole of fluoride. That comes from this balanced formula right here. So that's going to give me 0.012 moles of fluoride. Now I need molarity. That's what S is, and to do that I'm going to have to divide by my new volume. So very similar to some of those titration problems we did a few lessons back. So I'm going to take my new total volume and divide each number of moles by that, and I get a molarity of calcium of 0.1 molar and 0.04 molar for fluoride. So these are my S values. Now if I think about my KSP expression, remember it's going to be products over reactants, but it's going to be S times 2S squared because this is a 1-to-2 ratio, and we said 1-to-2s are always going to be like that. And now I'm going to plug in my values. Make sure I plug in the right ones. That tells me the KSP is going to be the concentration of calcium times 2 times the concentration of fluoride squared. And in fact, I can take, and I'm going to go ahead and erase this, I'm going to take the molarity out of the numbers because it's unitless still. So order of operations is stuff in the parentheses, then exponents, and then multiplying. So then I'm going to square the 0.08, multiply it by 0.1, and that gives me KSP is, oh, sorry, guys, I'm so sorry. This is Q. QSP is the reaction quotient. So we don't think we're at equilibrium right here. This is non-equilibrium conditions. Because I need to compare it to K. So QSP I get is 6.4 times 10 to the negative fourth. And now I need to go back up and get my K value for, what am I looking at? Calcium fluoride, which is 4.0 times 10 to the negative 11th, which I see that this number is bigger. This is the KSP. So when QSP is greater than KSP, the reaction shifts to the left. This reaction specifically, just to remind us, is this following, meaning that it favors the formation of solids. So yes, a precipitate will form. All right. So we're going to go back to something that's going to sound familiar, which is the common ion effect. Let me scoot you back over. And this is the last part in lesson 24. And then we have lesson 25 and then the test. So in acid-base equilibrium, the addition of a common ion, which is what we talked about with buffers, usually indicated the addition of the conjugate acid or base. In solubility equilibrium, it's going to just mean we're adding any other salt that contains one of the same ions. So if I had calcium fluoride and I added sodium fluoride, what they have in common is fluoride. So the solubility of AgNO3 is affected by the presence of AgI. Well, the ion that they have in effect becomes pretty straightforward when we look at these equations. The one that they have in common is silver plus. They do not have the anion in common. So will the presence of AgI increase or decrease the solubility of AgNO3? Well, in this case, if we are adding Ag+, what that means is it's going to increase the concentration of silver plus, which, if you remember Le Chatelier's principle, meant the reaction was going to shift to the left. So adding will increase the concentration of Ag+, which will shift the reaction to the left, which decreases the solubility of AgNO3. More AgNO3 is going to stay as a solid than dissolve. So let's look at how this could affect us with calculations. Problem 13 says, what is the molar solubility, S, of AgI in a 0.274 molar NaI solution? So in this case, we're looking for the S of AgI, and we have to think to ourselves, what do they have in common? Well, they have the iodine in common. So the common ion is iodine minus. In our ice table, we should know now that solids don't count. We're starting with no silver, because nowhere in the problem up here does it tell me how much silver I have, but we are starting with 0.274 molar of the iodine. Now, You might be tempted to say, well, this means the reaction is going to shift to the left, but remember, we know we have to shift to the right because we have to produce the silver. Right now we don't have any to consume, so we have to produce it. It's going to leave me with this. Now in this case, we're going to have our KSP is equal to the concentration of silver times the concentration of the iodine. Straight off the table, which if we look up our KSP value for silver iodine, and you do not need to memorize these, I will give you these on a test. Silver iodine, 8.3 times 10 to the negative 17th. That was not a very good color to highlight. 8.3 times 10 to the negative 17th. We're going to end up distributing the S into the parentheses, moving the KSP to the to the left-hand side. And you might be thinking to yourself, oh my gosh, that looks like a quadratic. And it is. But in KSP, because this value is so small, it's going to have very little impact on what S is equal to. So what we're going to do is we can assume that the KSP is equal to this, because whatever S is equal to is going to be so small that it's not going to have hardly any change on the value of 0.274. So, and we'll know if that's going to be right because we'll know what S is equal to. It's either going to be a big number or a tiny number. I'm going to divide out 0.274, and S is equal to 3.03 times 10 to the negative 17th molar. Okay, so that is such a tiny number. Okay, so in a sense, with that amount of sodium iodine present, very little of the silver iodine will dissolve. Okay, so that's common ion effect. That's the end of lesson 24. And there's just one more lesson, which is lesson 25, that'll be in a